Okay, next up, we have Paul he graduated from Purdue University, Civil Engineering. He worked with Professor Weiss on PoreShield development and now is with the Indiana Soybean Alliance.
And thank you for the opportunity to speak with you today. It's been an interesting session so far, and I think you've heard a lot of the things that I'm going to talk about as problems. Obviously, are going to be repeated to some of the other presentations you've heard, but hopefully we can not double up too much and get you some good information here. So just first off, I wanted to set the stage here by introducing the Indiana Soybean Alliance, who I'm here to represent, and why they're here and why they have an interest in preserving concrete pavements and concrete bridge decks. The Indiana Soybean Alliance is a checkoff organization. That money comes from farmers when they sell their beans to the market for the first time and goes into an organization both at the state and federal level with the goal of spreading demand for soybeans in order to drive the price up for soybeans and increase the utilization per acre of land we're using. So this technology, the research was funded not only by the Indiana Soybean Alliance, but now also the United Soybean Board at the federal level. So first, before we get too far into the technology, I do want to ask you to think differently. If you have any experience with this technology or with other technologies on the market like we've talked about today with silanes and things like that, it may look similarly when it goes down, but the way it functions is very different to these other technologies. So while it is made from soy, it is sustainable, it is very cost competitive. What we're going to talk about today is 100% performance. If there's no performance, there's no point to have any of the rest of the discussion, so we're really just going to lead with that. I know we're focused really primarily on bridge decks, but I wanted to lead you through the development a little bit because I think it's an interesting story. It was Purdue University and the Indiana DOT that was INDOT coming to Purdue and saying our pavement joints are falling apart way prematurely. It's costing us $1 million per mile to repair our concrete pavement joints. It's our critical factor in service life. If we can extend the life of those joints, we can extend the life of a lot of these pavements. How can we solve this problem? So Dr. Weiss and Dr. Tao at Purdue came together and thought soy methyl ester is a lot like the way we used to use linseed oil, only it's a lot safer and easier to use. It's readily available, abundant across the country. So they tried it and it worked very well. So some of those photos you see there are now INDOT implementing this in full-scale pavement joint projects. The one there at the top in the middle is US 24 in Fort Wayne, where they did new interchange there to create a free flow interchange, and they treated all the pavement joints on that one. And then the one you see there on the bottom left is I-65, a new section of mainline interstate heading right into Indianapolis, and they're treating all the pavement joints there. You can note the application method there is pretty interesting. They've got a roller wheel that sets right in the joint that helps them to spray so that they keep that as a controlled pattern with material going into the joint, as well as a 3-inch overspray consistently on each side. And then that bottom picture there is also the Sioux Falls in the city over there in South Dakota doing the same treatment. So after 10 years, we did field trials. This highway we applied it to was US 231 in Purdue. It was 13 years old at the time, so it had been heavily de-iced. It's a heavily traveled commuter highway. The pavement joints were looking good, but they were suspecting they were going to be vulnerable in the next few years. And the picture you see there of both of these actually is 10 years on from that. So now the pavement's 23 years old. The section that we've had treated for the last 10 years looks like the day we put it down. Those little black marks are actually the HMA fill we pulled out when we put it down, whereas the untreated section is starting to unravel in the way they see that deterioration across the board with their concrete pavements. The cement paste of that joint starts to crumble away and the joint widens up until you get the fun ba-bump, ba-bump, ba-bump when you drive over them. So what's interesting about this project and why I think I wanted to start with this and lead into bridge decks is that this is a different school of thought. In the past, most states with their concrete pavement joints and protecting those, especially in areas with de-icing salts, was Baccarat and self-leveling silicone or HMA fill, the goal being to try to keep the fluid out of that joint from the beginning, which we know that doesn't tend to work. A couple years after you put those in, you're going to start to see pieces of spaghetti on the highway where that joint fill is pulled out and traffic continues to pull it and pull it until it's gone. So this moves from trying to keep the water out of the joint to we're going to leave that joint open, let it crack to the drainage layer, let the water flow through it, but we're going to put the SMEPS or the PoreShield in the joint so that it soaks into the pores and protects the concrete itself. That way our water and de-icing salts aren't ponded in the joint. They run through the drainage channels we've designed, but the concrete itself is protected. The way this works, as we said, is different from a lot of what you've seen in the past, but it'll look the same when you put it down. Rather than making a coating on the surface, no chemical reaction will take place. So the biggest factor is the concrete is dry and those pores are available at the time you put it down. As long as the concrete's dry, when you put the PoreShield or the SMEPS on the surface, it'll soak in through capillary suction to the pore network, and it'll undergo no chemical reaction. It lives in the pores as a viscous, hydrophobic material that prevents water and salt from coming in. This means that it has some self-sealing properties. So if we've applied this to a bridge deck and then we experience some cracking in that first year, what's actually going to happen is the material liquid in the pores will move and migrate into the crack because the crack creates an access point for air, re-engages capillary suction, so it's going to move and fill into that crack and the pores around the crack. So you get really good long-term protection because it will move and adjust to accommodate what's needed. Just as a pause real quick, I know I've jumped back and forth between PoreShield and SMEPS. Just to let you know, PoreShield is not a commercially available product. It's simply a name we use to replace soy methyl ester polystyrene blends because that becomes a bit of a mouthful when you're in presentations like this. There are commercially available technologies you can buy that will have the PoreShield logo on the label, PoreShield inside, and it's licensed from the same patented technology. So this is a glimpse of what it looks like under the concrete. What we did here was put fluorescent dye into the material, let it absorb into the sample, broke it open, and looked at it under a black light. So you can imagine if that sample in the future is going to have water or salt put onto the surface, it's got a long way through the pores to go to get through that barrier layer we've created inside. And then that protection leads to really long-term durability. This is ASTM 672. It's actually extended if you're familiar with this test. This is run out to 70 cycles now, so 10 weeks of daily freeze-thaw. And we've increased the calcium chloride concentration. Primarily, when you're looking at the scaling test, you are concerned with this top layer here. That's what you're grading visually from 0 to 5 as you look through the progression of that test. All of these that are treated with SMEPS were 0 all the way through the completion of the test. You can see there is a little bit of roughness on the surface of the treated one because, again, we've done this almost 3 times now back to back to back, 672. So it's very, very aggressive environment with increased calcium chloride concentration. The real story, though, is when we take a core and we take high-resolution photomicrographs, and you can see what happens below the surface. Lots of damage and cracks in the untreated section. So regardless of the visual rating at the surface here, this untreated sample is going to experience rapid deterioration as we see progressive salt and freeze-thaw because all of that water and salt on the surface filters through all that damage and into the pores before it even starts the process. Whereas when we have the protection with the SMEPS, you can see even through all those cycles, there's no damage here to speak of. So all of that solution that we're putting onto the surface is held right there at the immediate surface. Similarly, when we do ASTM 666, we see very good results. The advantage of that self-sealing property, being in the pores and liquid and able to move and adjust as needed, means that we get an extremely long-term protection. Once we've gotten to 50, 100 cycles, typically things on the surface are going to start to break down and track more or less with untreated concrete, whereas our SMEPS samples maintain all the way through. I will add that if you want to investigate something like PoreShield or SMEPS in a test such as this, sometimes you will need to modify that test. This is a good example. ASTM 666, typically you would do cast your samples, 14 days moist curing, straight into the freeze-thaw chamber. Well, with the way the SMEPS functions, we can't get it into the pores unless we add some sort of a drying phase in there. We can't take a 100% saturated sample and treat it and expect to get protection because the water is blocking the SMEPS from being able to be absorbed. So in order to do a test like this, we'd have to take all of our samples, add a drying phase, a treatment phase, and then replenish that pore solution, typically with saturated lime water, before we would go back into the freeze-thaw chamber. So something I just wanted to point it out, because if you are within a DOT and you're looking at material acceptance or things like that, you'll want to be a little bit careful about what you're testing and that you are getting representative performance of this material, because if you don't have a section of that test that allows you to clear out and vacate some of the pores so that you can get the SMEPS in the pores, you're not going to get representative results of the performance you would see in a real-world environment where that does happen. This is actually data that you had actually seen from Dr. Kevin earlier, and this is from a Wisconsin DOT study where they evaluated the long-term performance. He had pointed out that 9X number. They also evaluated if you're using fly ash, like he said, to create good durable concrete and try to mitigate these issues on the front end, you would still expect a 5.4 times multiplier on your service life, which is really significant, especially when you're talking about the cost differences like we saw in the last presentation, where the cost to treat versus the cost to replace is a no-brainer. This is actually the same data he had showed here. When you look at the first half an inch of the samples that they tested, the PoreShield or SMEPS performed the best. Then the deeper you go, the better that performance kind of shined amongst the other products that they've tested. In terms of implementation, we've talked about pavement joints really starting to roll with the DOT. We've done unique special provisions in INDOT that's been used on quite a few contracts now, and we're working on the design manual phase that we hope goes into the Indiana practice next year. We were also part of the ITD TSP2 program. So we've done 3 field demonstrations, the first one being that Indiana DOT I-65 project I showed at the beginning, where they're treating the pavement joints. The second one being a bridge deck in Buchanan County, Iowa, with Brian Kylieber, who I'm sure many of you are familiar with. He's pretty active in bridge deck preservation. And actually a vertical surface application, if anyone would be interested in taking part in this program with us. We recently had our partner drop out. Our main hindrance here in finding a vertical surface application is finding a vertical surface we can apply to that we can also take a multitude of cores from without affecting the steel in the existing structure. So if anybody does have a vertical surface they'd like to do, we've treated lots of them and they seem to be working well, but to be included in the ITD program, we have to be able to go back and take cores for years out of a vertical surface. So if you are interested in that, please feel free to reach out to me and we'd be happy to discuss. Like we said, started with pavement joints, moved to bridge decks. It's being used in mortar patch material, both as an admixture and a topical treatment. That's actually a really interesting application, I think, especially when you have areas where you have a damaged bridge deck, say, and you're grinding down below that damage. You could be treating with SMEPS to protect the pores of that interface. Put your patch in, treat with SMEPS across the top to protect the patch and the surface concrete, and now everywhere you have potential for delamination, your pores are protected from water and salt. Also been used in precast material. One of the largest utility providers in North America in California has put us on their corporate-wide approved products list because they were pretty prohibited in what they were allowed to use, being based in California and having really strict VOC restrictions. Sidewalks, driveways, and patios. At this point, countless do-it-yourself and home projects, but major universities, Notre Dame and Purdue University. Animal barns are another application we've gone into. Hog slats are a very aggressive, corrosive environment for concrete, and it's done a great job of keeping those not only intact for the long term, but keeping the surface nice and smooth so there's not all kinds of nasty stuff in there. I don't know if many are familiar with hog barns, but they get power washed very frequently, multiple times a year. So having pieces flaking off and chipping off can pretty quickly turn into a devolving situation of deteriorated floor. Buildings, in particular salt storage buildings, have been a big one this year. We've done quite a few of those where people are putting in new salt storage units that are either concrete walls or block walls. Obviously a very corrosive, aggressive environment, so treating those goes a long way to making that building last longer. And then walls and parking garages. Really any mortar-based material. So if you have something that you're curious about and you think you could protect it from water and salt, reach out and we'd be happy to discuss that as well. As we talked about, performance is really the key there, and that's what I had mostly led with, but it is safe for the environment. There's no concern for overspray into water or land, no hazardous fumes, and it's a hazard-free SDS. Technically, it says no PPE is required. I think if you're working with any liquid chemical material, it's probably good practice to use at least goggles, but again, not required. You can see there in the GIF that is a 23,000 square foot bridge that they simply swept the debris from. It was dry the day of application. They were able to start to finish everything in 50 minutes. So you can see there's a truck with a tote in the back and 3 power sprayers. So they moved pretty quickly. I would say backpack sprayers are probably the most common for smaller bridges. We have done the bars on the back of the truck, spray bars, just like you'd seen in the other presentations, and pretty much anything. So we've even had folks tell us that have done indoor surfaces that I just put it down and squeegee it to where it needs to go. The nice thing about this material is it has surface tension much lower than water. That's how it penetrates so deep into concrete and gets into the pores. That means it's going to spread to where it needs to go. So imagine we have a bridge deck or a garage floor and there's a couple little low spots. We treat that area. Excess is going to pool in those low spots. You're going to get deeper penetration, better protection in the exact same spot water and salt's going to sit in the future. Again, like we said, it's 93% bio-based content. It is USDA bio-preferred, and it is on the federal mandatory purchasing list, which means that if you have a program that has even $1 federal on it, it should be considered as a priority over competing technologies that are not on the list. Emissions reduction, low VOC, 43.3 grams per liter puts it well below even half of the limit. The strictest limit in the United States is CARB, the California Air Resource Board, which is 100 grams per liter in this category, so we're less than half of even that. Non-toxic, like we said, safe, and no PPE. Again, if you have a vertical surface or really any application you'd like to discuss, please feel free to reach out. If you're interested in the technology and you'd like to hear me give a longer presentation, PoreShield.com has lots of good resources like that.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.